the rate of joining participants has slowed down, so I think we'll get started. Welcome everyone. Good afternoon, good evening, good morning, wherever you are. We have an international audience here. I'm Rich Kleidman. I'm the CEO of AirPhoton. I'm here to introduce today's webinar, which will be presented by Dr. Konstantin Kuznetsov. You can see the title here. This is Modeling Street Level PM Dispersal. And I just wanted to make a few introductory comments because perhaps not everybody is familiar with GRASP Earth. Next slide, please. So you may know us as separate entities, GRASP SAS, which is in Europe, and AirPhoton, which is in the United States. GRASP is known for the GRASP inversion platform, as well as many algorithms that are used by European space agencies and production of products from many satellites. AirPhoton is known mostly for designing, creating, and selling high-end instruments for measuring airborne particulates in situ, so either at ground or an aircraft. And in the summer of 2022, the two companies merged, and now we are doing business as GRASP Earth. Next slide, please. So the reason for the merger is our shared and greater mission. And what is our mission? Our mission is advancing the study of Earth's atmosphere. So particulates, clouds, surface properties. We're even now getting into the business of trace gases. And we're advancing this study of the Earth's atmosphere with a multi-pronged approach. So satellite data. This is commercially available satellite data from the various space agencies, some of which has been processed and is archived in GRASP's own archive, as well as our own satellite data. We have in process a mission we're calling Climate, which will have both a polarimeter and a spectrometer. Instruments, the AirPhoton instruments that I measured, as well as modeling, and a synergistic combination of all three elements. And this is something that NASA and other agencies have been after for a long time, is this synergistic combination of all of these elements in order to improve our capabilities, not only for understanding climate and climate change, but also for understanding air quality. And so we are assembling many pieces of this. And one of these pieces is today's work that will be presented by Konstantin. So next slide, please. So let me just say a little bit about Konstantin and his background. So he completed a Master's of Applied Mathematics in 2010 at the Nizhny Novgorod State Technical University. He has a PhD in fluid mechanics, which he completed in 2013. His focus was nonlinear wave dynamics. In 2014, he began working as an associate professor at the RUDN University in Moscow. And then in 2016, he relocated to Paris to work at the Institut Polytechnique. And since January 2022, we've been fortunate enough to have him as a member of GRASP. Today's presentation, it's a model study, but with very practical applications to advancing our mission of the synergistic use of various data sources. Today, Konstantin will be discussing 3 sample cities where he's done this work. I have a makeshift map here. I think most people know where Warsaw and Paris is. but the third marker here is for Valladolid, Spain. And I don't know if everybody knows where that is, so that's why I'm showing on the map. Now, even though our focus here is in Europe, note that we can apply the techniques that you'll be seeing today to any city, large or small. And with that, I think I'll turn it over to Konstantin. There was a message waiting in the chat for you, but we've left plenty of time for questions at the end. So please do put your questions in the chat and we'll try to get to them in the order we receive them. And don't worry, you'll be able to ask additional questions at the end. So with that, Konstantin, take it away. Thank you.
Thank you very much, Rich, for the introduction, and thank you everyone for joining this webinar. The topic of my presentation, as Rich was saying, is simulation of PM dispersal on the street level, or urban scale simulation of aerosol. Let's talk first, what is urban scale simulation of aerosol transport? First, physics of aerosol transport is a very complex multi-scale problem with scales from millimeters to dozen kilometers, and it has for different scales it have complex combination of complex multi-physical processes like turbulence, advection, diffusion, radiative transfer, heat exchange, and chemical reactions. And there are different models that trying to take into account some of these effects at least. And all this model we could classify into three groups. The first one is most popular group, I would say, Gaussian plume models. It's like IDMS or AirMod. Most of operational models are using this approach, Gaussian plume models approach. It's almost has it has very low computational cost in these models, but do not take into account many effects like complexity of buildings, etc. The next group of models, which is more complex, the Gaussian one, is street and grid models, which is considered that the different variables of pollutant is constant along some streets or segments of streets. And Munich is one of this model. And then the next group is the big group with CFD models. This is like a big gun to solve any fluid mechanics problems. As an example of these CFD models could be OpenFOAM, ANSYS, PALM, which is specific for atmospheric applications, and Code Saturn. And we are using Code Saturn, which is open source code developed primarily by Electricité de France. Let's focus on the urban scale CFD simulations and its advantages, disadvantages, problems associated with this application of this approach. First, about advantages. First of all, this approach allows us to resolve all variables, all physical variables related to the dynamics of the air, velocity, temperature, turbulence variables in the calculation domain with high resolution, 1 meter, even like centimeters around some buildings, if you have enough computational resources. It could take into account complexity of buildings, geometry, take into account turbulence, different types of surfaces, water, roads, vegetation. Optionally, we can include trees and bushes. But it has as well some problems that make it difficult to apply this approach for aerosol transport. First problem is fragmental knowledge about geometry of the urban areas. And basically it's combination of two with high requirements to the quality of geometry for mesh generation. We need very high, with very good knowledge about the geometry of buildings, which is not the case in many situations. And computational, the other problem is computational cost, because that's the more accurate the results, the more computational resources it requires. And the other question is that it's very important to use proper initial and boundary condition. Sorry. Let's talk how we solve these problems in order to apply these methods, CFD simulations, to the problem of aerosol transport in the urban areas. For that, we're using automatic mesh generation tool. This is our own tool developed here. It helps us to solve first two problems. First, we need to prepare the data, geodata, about the calculation domain. Here we're trying to collect all the data available. In the best case, it is LiDAR measurements of heights and OpenStreetMaps with high resolution. Usually for big European cities, 50 centimeters resolution are available publicly. And later we need to pre-process all this data in order to separate, because usually these LiDAR measurements has heights and they are not separated. Like here we can mix up trees with buildings and we need to separate them somehow. For that, we need to apply machine learning algorithm like unsupervised classification, K-means, etc., or the other more complicated algorithms for that. But here's the example for Warsaw, for example, how we separate trees on the left, buildings on the left side from trees, the height, and the different land cover. So we have to prepare all these few layers for our next step to generate mesh. And later we preparing the Cartesian grid of the terrain with the elevation of the terrain with a resolution of 32 meters. This is the basic resolution for our model. And we refine only important zones. It could be, for example, zones around buildings, around monitoring stations, etc. Later, we remove cells from our mesh corresponding to buildings and add different boundary zones needed in the computational case. For example, it could be water zones, different roads, or for example, parkings. And here's the example of mesh was generated using this with this approach, with this tool. Here is example of mesh for the area 1 by 1 kilometer in Warsaw. The gray area here is buildings. Green is vegetation. Brown is road, and yellow is parking, so open areas. And the behavior of fluid will be different on different surfaces. And you see that for open areas, so for example, here we have lower resolution, or around buildings we have finer resolution. Here another example of mesh for Paris. Here is more types of different surfaces, but the same approach. Once the mesh is generated, we can move to the next phase, is to phase of dynamic simulations, to simulation of wind velocity in the domain. For that, as I remember as I remind you that there is the other problem to set up the proper initial and boundary condition, because the calculation domain is very strongly depend on this boundary and initial condition. So we choose here the typical approach, I would say, because this is Money-Noble similarity theory, and we define the boundary and initial condition on the domain according to this theory. Using 4 parameters: friction velocity, ground temperature, and Money-Noble length and wind direction, with different combinations of values of these parameters, we can describe almost all meteor conditions in the area. For sure, there is some limitation of application of this theory. First of all, this is valid for the less than 1 kilometer height. It could be valid for high altitude, but there is no theoretical foundation for this. So, so here we consider this approach, but this approach usually working well on the lower atmosphere. The next is once we apply this boundary and initial conditions, we can run calculations and see the dynamics of the velocity, of temperature, and different physical variables in the domain. And here's how it looks like, for example, for center of Paris. This is an example of dynamic boundary conditions taken from the real meteor stations, because usually the forecast defined on the larger areas. Here is 2 by 2 kilometers area, and we consider that boundary condition is homogeneous in this calculation domain. And in this case, we can resolve very accurately what is the velocity field in the whole domain. For example, here you can see Notre Dame. Behind the Notre Dame, for sure, it's blocked the wind. The velocity magnitude is lower. See the red color showing the higher velocity magnitude, the blue one showing lower velocity magnitude. So we can as well model different all different physical properties for the domain, like temperature, aside velocity, temperature, turbulence kinetic energy, turbulence dissipation rate, all the parameters that describe the dynamics of the air completely in the computational domain. So once we have resolved velocity field and defined all the dynamics variables in the computational domain, we can move to the next step, to the step of the aerosol simulation. And here's the model of transport of aerosol transport model that we are using. This is a pretty complex model, but still linear. I will not go into very big details, but just showing that we are taking into account, if if we consider only black terms, it will be like a typical advection diffusion equation for passive pollutant. But here we take into account for example, red term, it is gravitational settlement velocity. In the blue one, inertial term. the turbophoresis and thermophoresis, this is to take into account that pollutant has a tendency to go to the zone of the lower turbulence and lower temperature. So we take into account that as well. And we could take into account the position near the surface, the position of the aerosol. And all these parameters depend on the density of the particles and diameter. And very important note that this model is pretty complex, but still linear. It's linear with respect to the velocity. Velocity field is strongly nonlinear, but the dynamics of pollutant is still linear. We will use this fact later. And here on this picture, we have an example of the pollution field in Warsaw. This is PM.3 from one road in Warsaw. This is how it looks like, one snapshot, just an example of the calculation. And one of the main topic, we move to the main topic of the presentation, how we can combine satellite measurements with ground-based measurements to retrieve road emissions and pollutant on the pedestrian level. Is that possible to do that with help of the modeling? Let's try to solve this problem. To do that, we are considering an example of the medium-sized typical European city. It is Valladolid in Spain, and we take the domain 1 by 1 kilometer with 800 meters height in the area. This is how it looks like bigger. We put 6 ground-based sensors. This is virtual experiment, I would say, but on using real data of the city. We extract the road network from OpenStreetMaps and place some randomly placed 6 sensors in the zones. They are marked by red dots. And following our previous steps, we generate mesh for this area and run calculation for the fluid phase in order to describe dynamics of the air in the area. So here we use some advanced second-order turbulence model, and the simulation is, because the mesh is pretty good quality, it was relatively fast. So once we've done this simulation for fluid part, or like the simulation of the movement of air in the area, we can move to the next phase, to the simulation of the aerosol in the area. Here we, for the aerosol transport phase, we're considering 25 road segments in the area. And the model pollution dynamics separately, and we model pollution dynamics separately from them. Like consider that every road segment is kind of isolated one from each other. Here is to give an example of the pollution from one road. This is on the right side. You can see the picture of this road of the real city, just to give you a sense of scale of the problem. And on the left side is the dynamics of the pollution field at the pedestrian level at 2 meters height with 1 meter resolution, I think. And let's clarify further the all assumptions we made to simulate pollutions. First, here we focus on one beam of the PM particles. Here, for example, PM.3, but we can choose the other particle as well. But for this particular exercise, we fix one particulate matter. The other assumptions that all pollutant in the domain are defined by the 25 road segments and the boundary, and we consider them isolated. Couple of words why it is legal to take these assumptions. Because as I was saying about the aerosol transport equation, it is linear. So we can separate them out and use some combination of these roads without losing the generality, without losing anything from the model. We can multiply by some factor, we can sum them up, etc. The next assumption is we could consider that the emission is constant along the road segment. This assumption is also pretty popular, even there is some particular class of models, for example, Munich or street and grid models that have this assumption as a very basic one. They do not consider only emission constant, but also the pollutant field is constant. But in our case, pollutant field can be completely different along the road, but the emission is exactly the same. We consider that the traffic is relatively similar along the road. The next assumption is steady state meteor conditions for 20 minutes period. This is as well very popular assumption, and we can see that in reality the weather conditions really do not change much in 20 minutes. 10-20 minutes, I would say. And we don't take into account here nucleation and chemistry processes. So we consider the period of propagation of the field that in the domain 10 to 20 minutes, and we consider that in 10 or 20 minutes the domain will kind of renew completely. And the changes coming from either from boundary conditions or from the road segments or predefined sources. Using these assumptions, we generated a synthetic pollution field in the area by linear composition of the pollutant from 25 streets in the area. This is how it looks like on the pedestrian level. And we predefined emission values for every road segment. Next, based on the generated pollution field in the area, we can calculate the LD from this pollution field, because we know all the values in the domain, all the values of concentration in all the domain. We can integrate them along the height and calculate LD measurements for the total for the total concentration field. And so we have generated LD measurements. We have measurements from the ground-based stations. And the question is how to having this information about LD measurements and ground-based stations, how to reconstruct the pollution field concentrations on the pedestrian level at 2 meters high with very high resolution, 1 or 2 meters, how to do so. To answer these questions, let us formulate this problem in mathematical way to make that very clear. We can define a few variables. First, we define vector of the emissions, Q, Q1, Q2, Qn, and here in our case is 25 different sources, isolated sources. And C is the pollution field from these isolated sources. The one that is calculated from aerosol transport model. LD is a linear, is the linear operator to estimate aerosol optic of depth from pollution field. Operator G is the linear operator to estimate ground measurements from the pollution field, because we can calculate, we can estimate aerosol optic of depth if we know all pollution field. And as well, we have two given vectors of aerosol optic of depth measurements, for example, which coming from satellite or I don't know, Ironet station. And G is a given vector of measurements from ground-based sensors. The total pollution field, as I already said, could be described as a linear combination of the isolated sources multiplied by emission factor. If we sum up all this pollution field, we will have a total concentration. But operator LD and G, this is a linear operator, and we can apply them, both operators, to this equation 3. Basically, it will change nothing. So if we do so, we can write 4 and 5. In this case, coefficients or emission factor Q1, Q2 is exactly the same, because they reflect the same reality. The different aspect of the reality, but the same. And we can put them in one matrix and create a system of linear equations to retrieve emission from roads. And we can write this system of linear equations. Here, LD could be really few LD measurements for the same period of time, and G as well, few ground-based measurements in the period of time from every isolated source. And solving this linear system by, for example, least square method, we can find the Q1, Q2, Qn. So let's move from mathematical formulation to implementation of this approach. And for implementation, we can define for every road segment in the area, we can define the pedestrian footprint of the pollution field from every road. This is the basically pollution field at the pedestrian level at 2 meters high with 2-meter resolution. This is a snapshot. You see that different roads has different pollutant field. And we do the same LD footprint of the pollution for every road. Here we have 100 by 100 meter resolution. So for every road, we define this LD footprint. This is exactly the linear operator LD CI. If we coming back to mathematical formulation. So, and when we solve the linear system of linear equations, we can we can compare the retrieval of emission factor from satellite, from sensors, and the combination of satellite and sensors. If in case we have ideal situation, no noise on satellite, no noise on sensors, we have an ideal retrieval because this is an ideal case. So let's add 20% noise to satellite measurements, to our, not satellite, but AUD. Here is still we can able to retrieve the emission factors for every road, pretty close, I would say, if we use 20% noise on satellite. If we add just a little noise, pretty neglected, the sensors, the ground-based station can give a wrong information. I would tell you why later. If we combine satellites plus sensors, the error for sure is lower when if we just using satellites because we have more information when we are retrieving. And here's the exact values of the emission. The blue one is predefined emission factors for every road. For example, the road of Hispania have emission factor 1.25, but retrieved one is pretty close, 1.6, I would say. And you see it's good, really good comparison, really good matches. So using this approach, we can as well reconstruct the pollution field at the pedestrian level with 2-meter resolution. So if we're using the synthetic AOD with 20% error, the error of the pollution field at the pedestrian level will be just 8%, so it's even less. Let's do the same exercise, but only with ground-based stations. We have 6 ground-based virtual sensors in the area. And we are trying to retrieve exactly the same number of variables, same emission factors, but as you can see here, they completely off, and they generate completely wrong pedestrian, the pollution field at the pedestrian level. And you see that the error is like really 2000%. It's completely wrong. So it's less accurate, less robust, I would say. Not less accurate, but less robust. Why is that? It seems to be like not logical conclusions that some LD measurements can provide more robust insight about emission roads than ground-based simulations. But the answer is pretty easy, because depends on the placement of the ground-based stations. So, for example, if our wind is coming from north to south, but the source of our pollution placed here, for example, this is that road of the Valladolid, the all pollutant field is coming from north to south, and all our ground-based measurements just don't see any pollutant field from this road. But in fact, it is there is a pollutant field from this road. So, but satellite measurements can cover all the area, and this way we can, so it doesn't have this this feature because we cover the integral value of the whole area. So we come into the conclusions. Framework to construct a CFD digital twin of urban pollutant could be applied to any city. It is possible to retrieve road emissions from all the observations, which is proved on this synthetic exercise. Satellite observations, if we have enough measurements, can provide more accurate retrieval than the ground-based sensors, just because it's an integral value for all the area. And for sure, the construction of advanced digital twin of urban winds based on CFD is necessary to solve this problem. Thank you very much for your attention. Here's the references. If you have any questions, I will be happy to answer.
Thank you, Konstantin. So if people do have questions, we prefer if you put them in the chat, and then everybody will have an opportunity to see the question, and then we can go ahead and let Konstantin answer. While we're waiting for any questions, maybe we could advance to the next slide. One more, yeah, one more. There we go. Oh, sorry. There should be a slide at the end. We have a third webinar coming up in November. It's Oleg Dubovik will be giving a talk. It will be an introduction to GRASP Open, but it will also include some practical applications that might be new to you, especially if you did not see our last webinar. Our last webinar was on how Dr. Chong Li developed a method to derive dry PM 2.5 mass from our optical nephelometer measurements. The presentation, Oleg's presentation, will be on November 5th and 6th, but we will send out an email to all of today's participants, and we'll provide that information and also a link to a recording of today's presentation. Oh, okay, we do have our first question. I'll read that out. It's, what EOS satellites do you have in mind for retrievals at the street level? And do you expect to be able to retrieve PM 2.5 directly or only via AOD? How will this transformation be performed? So let's start with that question. Konstantin, is that something you can answer for us?
Yes. First, yeah, let's, well, what EOS satellites? First question about what particular Earth observation satellites do I have in mind? I'm not a specialist in the remote sensing, so I don't know the what kind of what is the particular type of observation satellites we can use for that. For me, I consider it as a LD, that we already have some LD for. I already have LD value for the area, and this is what I'm using. Maybe the other my colleagues can answer to that question. What particular type of Earth observation satellites could be best for that?
Yes.
Yeah.
Can you hear me?
Yes.
So right now, what we are doing is using Sentinel-2, Sentinel-3, and Sentinel-5P for the retrieval. We are also considering to use HARP as multi-angular polarimeter right now in the space. And what we are doing is, with GRASP, combine all satellite measurements into a single retrieval. Probably in the next webinar, Oleg will talk about this concept.
Okay, thank you. David. Then what the other question is, what do you expect to be able to retrieve PM 2.5 directly or only via LOD? I expected that what I able to use, I would say in this words, able to use integral values of PM 2.5 from 0 to 1 kilometer or from 0 to 3 kilometer. Higher than 3 kilometer is hard for me, but from 0 to 3 kilometer. But what I need, like I want to have an integral value of PM 2.5 in this in the domain. That with this value I can work with high resolution possible for sure. If it's it seems 100-meter resolution is good enough. I did exercise on 300-meter resolution. For sure, it's works not that good, but still can provide some valuable information. How this will transformation be performed? For that, I think it's also more a question to people with remote sensing background, how LD could be converted to PM 2.5.
Yes. Yes, and maybe I can add a few words. So right now what we are doing is to retrieve from the satellite total column information, and we are working in different strategies to transform this total column information into PM. Of course, there is limitations, and we have to use some assumptions. There are several strategies. For example, we can use ground information. We have a combined retrieval ground plus satellite that we are exploring. Another strategy is use external assumption from modeling like CAMs. Another assumption can be use AI tools for transforming the total column into the final product of PM. This is something that we are exploring, and probably we will give another webinar about this topic, showing you all our efforts in the different directions that we have done.
Yeah, but here I have to know that I don't need like really, because usually when people talk about PM 2.5, they talk about PM 2.5 at the pedestrian level. What I'm talking about the PM 2.5 in the integral value in the column. So it's more LD with some factor, because LD it's already integral value of some particular matter. But what I don't know personally, how to separate out one particle from the other particle, but for that, this is not my area of expertise. The next question is on the slide 26. 26. If I got this, only hold it if extinction is constant and identical for all sources and background aerosol. What extent is the source of uncertainty? Is if extinction to road mass is constant and identical to all sources. Yes, because here I mentioned that we have you're right, because we are considering that have an assumption that we are focusing on some one particular type of PM, for example, 0.3 or I don't know 2.5, but we can add them as a like we can in our retrieval we can use few bins for sure, but it will require more values of the information, more values of IOD. So that's do I answer your questions? Your question? This is it enough?
Yes, this is Martin. Yeah, I think so. That I mean, obviously, if you have, for example, if you have exhaust pipe emissions versus resuspended dust, you expect completely different size and AOD to extinction ratio. But of course, if you have enough remote sensing data to maybe get disentangle this and have multiple size spin in your retrieval, then that can work. But of course, it will increase the uncertainty of the remote sensing approach. And if you, and maybe there, if you have well-placed sensors where you can get additional information, in the end, the combination would probably be best in any case.
Yeah, I agree. Thank you.
In some way, it's a little bit biased towards the power of the satellite retrieval. Also being maybe also points like that you don't get the data when you have clouds, and you may have relationship between pollution level and having clouds or not. Things like that are certainly also important.
Yeah, thanks. But yeah, here we consider that we are able to separate one beans and one beans from the other. It's like to say that from satellite measurements we can. I assume it, but we are able to say that some particular bean of PM have this integral value in the column, some particular value. I don't know what it is, but this is what information I need.
So you run the satellite retrieval, which gives you PM size spin or size spin resolved AOD, and then the equation 4 would hold more exactly.
Yeah. Okay. Yes. Thank you for the question. Yeah, the next question. Many thanks for your interesting presentation. Thank you. If I understand correctly, you don't need local sensor for having this simulation. Yes, I don't need the local sensor to perform this simulation. What I need is information about heights. The best is LiDAR measurements. Usually some geographic agency of Geography Institute of every European country, they provide this kind of information, and it is possible to get this information from them. This is the only information needed. It is possible to do it only using with only OpenStreetMaps, but the data in there very often not very accurate. So the best it be the combination LiDAR measurements and LiDAR measurement of heights of buildings, so digital surface model and digital elevation model. Yeah. Okay, seems I answered. Thank you very much for the presentation. Thank you. It is currently possible to obtain data of this caliber in the open source way by any researcher who needs it, or this is something that intended to be done in the future. It's yeah, the data of modeling is available. I think it's not yeah, so I think you can write me an email what kind of information you need exactly, and I will answer. Send it to you what is exactly needed. Yeah.
So thank you, Konstantin. Just I wanted to make a couple of comments. So in response to Martin, yes, this is a very satellite-centric approach, and as a in situ instrument guy and also a satellite guy, I think we all know that the best results will happen when we can combine the ground data with the satellite data. And we are working on projects of that kind. And as David said, that will be a subject for a future webinar. But we have a project currently with a partner in India who's a manufacturer of inexpensive ground sensors. And we're working with them in Bangalore and Ahmedabad to develop what we're calling hyperlocal PM data. And so we'll be using ground data to inform the satellite retrieval, as well as satellite data to inform the ground retrieval. Also, a practical application of Konstantin's work is because we and others, we now provide our sampling station now has the capability to sample by wind direction, but we know that if you're using that for determining sources and source apportionment, you really have to understand the local dispersion field. And so this is something that we'll be providing as a service on request if folks want us to do this dispersion modeling to help them select better sites, either for an individual instrument or for a network of instruments. And last but not least, I wanted to mention to Sama that we are starting to work with organizations in Saudi Arabia, specifically for desert dust measurements. And I think we'll be more involved in that part of the world going forward. So with that, I don't see any additional questions. I did see that Konstantin mentioned that publication is in progress, so we'll make sure to send out a mail message to everyone when that publication comes out, and we'll let you know where you can get that. Konstantin, any final comments before we go?
Yeah, that's just a comment again about the last question about Sama, about the application to send semi-desert roads region in the satellites data only. Yeah, just yes, I think it's possible to answer it for the question to highlight. Yeah. Well, the other is thank you very much for your interest. Yeah.
Yeah, thank you everybody for joining us today, and thank you, Konstantin, for a very interesting presentation.
Thank you.